Hi, welcome to my talk on the application of CryoTEM for studying protein metal organic frameworks. My name is Joe Patterson. I'm an assistant professor at the University of California, Irvine, in the chemistry department, and the work I'm presenting today was largely performed by Alana Ogatar, who is a former postdoc in my lab who is now at Harvard University. Okay. So I think many people are familiar with metal organic frameworks. They are three-dimensional porous structures constructed using organometallic chemistry, so with the bonding between metal atoms and organic linkers. And these materials have been widely investigated and are used in many different types of applications, such as storage, sensing, and things like that. And all the applications are really related to the fact that they have extremely high surface area and very well-defined nanoscale pores for either encapsulating or not encapsulating specific molecules. So protein metal organic frameworks, as you might guess, is then the incorporation of a biomolecule like a protein inside of this framework, as you can see here. And the protein that I'm going to be talking about today is larger than the pores, and so really I kind of think about this as sort of occupying defects within the frameworks. And again, these systems have been widely studied. I've put some references up on the slides. And from an application point of view, they've been shown to be, again, really interesting for things like catalysis. So in that case, if you encapsulate an enzyme, it's been shown that the metal organic framework acts as a protective coating around that enzyme. So in situations where it might normally degrade very easily or degrade over time, the MOF protective coating protects this and allows it to function as an enzyme under conditions where it wouldn't usually, and that's very useful for taking enzymes and using them in industrial chemistry situations. So again, that's been really well studied, but what's been less studied, I would say, is how these materials actually form and what influence that has on the properties. So you can imagine, again, if this is an enzyme, the substrate for which the enzyme has to act on needs to get all the way through the framework. It needs to find the active site of the enzyme. And its ability to do that is going to be really dependent on really kind of the specific orientation of the biomolecule within the framework and also kind of the surrounding architecture. And so in order for us to control that, we really need to understand how these things are formed. And there have been some really nice synthetic methods developed, which really just involve mixing the proteins in aqueous solution and having the MOFs crystallize around them. But the details of that mechanism have not been perfectly elucidated. And so that's really the focus of the study that we're going to talk about today. And so, of course, already ahead of time, you could kind of imagine that these things are going to form through a non-classical nucleation mechanism, which is the case. It's not so surprising. And it's really worth highlighting that these non-classical nucleation mechanisms have been really widely studied. This is probably my favorite kind of review paper on the article. If you're interested, and I would definitely recommend going to read it. And so what is really well known for these systems is that, the mechanism by which you go from your kind of precursor ions or atoms to your final crystal can be through many different types of pathways. And the specific pathway you take and the specific details of that are going to affect your final structure and properties of the materials. And again, this has been really, really widely studied for many different types of crystals. But for these protein metal organic frameworks, it's not really been studied very well. What we know from many other studies is actually that CryoTEM is hugely important here. And I always say it's important for several reasons. The first reason is just a general microscopy perspective. So having a direct observation of these precursor states allows you to understand their role, when and how they're present in the synthesis. And so direct observation is really important, especially when you start to get multiple different types of structures appearing at once. And so TM is really good at helping to identify that. The second area where CryoTEM comes in as particularly important is because really all of these precursor phases, or many of the precursor phases, I should say, can have a very hydrated or solvated nature to them. And so if you were to dehydrate some of these phases, it would be completely misleading as to what their actual structure is. So particularly for liquid droplets or many of these kind of amorphous nanoparticles or amorphous solids, they contain a significant amount of solvent in them that's going to be really important to their structure. So CryoTEM is known to be a great method here, and that's also why we wanted to exploit it to study these systems. So in order to really answer this question about how do these systems form, we first wanted to study the growth of just the metal organic framework in water by itself. And so I want to point out, I have previously studied the formation of these systems in methanol, which is their most common solvent of synthesis. I did a liquid phase electron microscopy study on them when I was in Nathan Gianesky's lab. And many, many other people have studied ZIF-8. It's probably the most well-studied MOF, but almost all of those studies have been in methanol. And for these biomorph systems, they're very often made in aqueous systems, I think for obvious reasons. And we actually discovered that there've been a lot less done on how these form in water, and it turns out it's actually pretty different. So we wanted to study just the ZIF-8 formation by itself first. So the way this works is you take your methyl imidazole and your zinc substrate, so typically zinc acetate, you mix them in water. The ratio that you mix them is really important. To start off with, we're going to talk about this ratio of 35:1. And over a time period of 24 hours, you get these crystalline precipitates, so very beautifully faceted crystals of a variety of different sizes, which using powder X-ray diffraction, we can confirm are indeed the well-known ZIF-8 structure. So by CryoTEM, we studied this formation process, and essentially we just take aliquots at different time points, vitrify them as soon as we take them, and then study them later in the microscope. So what we found for this ZIF-8 only system is that really after very short time periods, just a few seconds, you start to form these amorphous particles. And I should say in this case, we're really defining what we mean by amorphous as the lack of crystalline structure observed in real space. Because the MOF lattice spacing is quite large, as you can see over here, 1.3 nanometers, it's not that challenging to observe this in real space. So we didn't do any diffraction in this study because it was actually quite easy for us to observe the crystal structures in real space. Well, not that easy, but it's possible. So anytime I say amorphous here, that really means a lack of observed crystal structure. So we formed these amorphous particles initially, and then over, again, a relatively short period of time, a few minutes, they appeared to kind of aggregate and almost redissolve into a second kind of solid or liquid-like phase. And what we can still see the kind of appearance of these particles, but it looks like they're more blended in with the background, which indicates that there is some exchange process going on with the particles and the background to sort of compositionally match them. And then as we go even further in time, what we find is we start to form these ZIF-8 crystals. So particles that have a structure, which is remnant of that of a ZIF-8 crystal. And also they have the lattice spacing completely conform with ZIF-8 as a crystal as well. And we only really saw these crystals appear out of this kind of aggregated dissolved space. So we really believe that this kind of the creation of this amorphous region is really key to the crystallization process. We didn't observe any sort of small crystals forming in the absence of this. So one thing I really want to point out here, which is a kind of important consideration for CryoTEM that I think most people who do CryoTEM realize, but often we don't talk about it. And that's the fact that when we make our CryoTEM samples, we are actually selecting, in most cases, a very specific part of our sample. So when we prepare our CryoTEM samples and we make these thin layers of liquid on our grid in our holy carbon grids that we vitrify, we very often exclude very large particles. And that was certainly the case here. So what we tend to do in my lab is we always also perform regular dry state TEM analysis in conjunction with our cryo analysis to see if there's anything that we're kind of excluding with the cryo prep. And that was certainly true in this case. So in many samples where the CryoTEM sample appeared to be you know, this kind of relatively homogeneous field of these amorphous precursor particles, or as they start to aggregate together, dry state TEM analysis would show us we already had very large formed ZIF-8 crystals. And so I want to point that out here because what this shows, which is also something that we find or indicated by other analysis, is that the growth of these crystals is very rapid compared to the kind of nucleation of them. And at really any time point that we sample this, we can find evidence of different stages in the formation. And what I'm really tracking here, or what Alana was really tracking here that we're showing you in the cryo images, is really just the bulk average changes that we see. But that's not the full story because, like I said, it's slow nucleation, fast growth. So that's really important to remember. Okay. So then we move on to the addition of a protein into the system to see how that affects the growth. And the protein we use to study here is bovine serum albumin. And it's the most commonly used kind of model system for these protein MOFs. And that's why we picked it. So the really only addition to the synthesis here is just the addition of this BSA. Typically, we add that in first with the imidazole precursor, and then we add zinc to induce crystallization. What we find in this case at the end of our 24 hours is we have a very different situation. We have much smaller crystal structures, and we no longer have these very smooth, beautiful facets. We actually have this quite rough surface structure here. Again, the XRD confirming for us that we still have the ZIF-8 crystals. And really importantly here, high resolution dry state TM is showing us that these are single crystals, and that even this kind of rough surface structure, which you can kind of see here, is really part of the crystal phase. It's not an amorphous coating on the surface. This is really a single crystal. So how do these form, and how is it that the biomolecule is able to manipulate the nucleation and growth process in order to form these completely different types of crystals? So again, obviously we turn to CryoTEM and we sample over time in the same way that we did before. And this time what we see is a different picture. So in the early time points, we actually start to see lots of very, very small particles that are starting to aggregate together. So in the 4-second time period, we can kind of see, if we zoom in, we have these very small, roughly about 7 to 8 nanometer particles, which we think are the protein itself. It's a 7 nanometer protein. And then over time, what we find is that they aggregate into these kind of branch dendritic-like networks. But if we zoom in on those networks, we still see these kind of individual 8 nanometer particles. And so we wanted to look at this in more detail. And so what I'm showing at the bottom of the slide here is a composite image of about 40 of these sort of roughly 8 nanometer looking particles here. And we've made, we aligned them all, cross-correlation aligned them, and then averaged them together to get a high signal to noise image. And what we can see when we do that is, you know, right at the very edges, we have this bright halo, which is a defocus artifact. But then as we move closer into the center of this, what we see is a core shell structure. So we see this kind of light gray shell around this very dark core. And you can also see that in the plot profile analysis here. We have this, these turning points in this, which is indicative of this kind of core shell structure. And the core here looks to be, yeah, like I said, exactly 7 nanometers, which is the size of this BSA. And we think this shell is really just a shell that is a mixture of the methyl imidazole and the zinc ions. So this is kind of coating the surface of these particles and then really controlling their charge interactions, which is enabling them to kind of aggregate together into these networks. Just as a kind of comparison, this is a similar analysis done on the ZIF-8 only sample. And so the amorphous particles that we found in that sample are actually almost exactly the same size as these, but they don't display this core shell structure. They're much more kind of homogeneous. And so again, I really believe that the core we're observing here is the BSA molecule in this case. So as we follow this through in time again, what we actually find is that the crystalline particles, the ZIF-8 crystals, appear to grow in the presence of this protein amorphous network. And we kind of, almost looks to me like the protein amorphous network is wrapping around these ZIF-8 crystals as they form. And again, we did high resolution imaging of this. So this is high resolution CryoTEM. And what we can see is kind of within these networks, again, we have lattice spacing, which is conform with ZIF-8. And this lattice spacing extends all the way out to the kind of jaggedy edges of these particles. But if we move even slightly away from the surface of these crystals, we don't see any lattice spacing anymore. It's actually not that clear in this image, but there is a particle inside this box that is not displaying this lattice spacing. And indeed, we could never find any evidence of these particles being crystalline until they come in contact with this surface. And so we really think this is kind of an attachment of these precursor particles that then crystallize on the surface. Again, a process that's very well known in other types of crystal structures. So from the CryoTEM analysis, our kind of observation here is that we grow these crystals. We grow what we think are just kind of regular ZIF-8 crystals. And then at some point, this protein precursor network surrounds these crystals, stick to the surface, inhibits the growth, and then you get crystallization of these on the surface of the growing ZIF-8 crystal. And so we wanted to check that, and we did that by performing the same synthesis, but with a fluorescently tagged biomolecule. And when we do that, we find these ZIF-8 crystals that clearly have this, again, core shell structure, indicating that the biomolecule here is really just on the surface of these, it's not throughout. So this is very supportive evidence of what we saw in the CryoTEM time series. So just to summarize up, what we found is that we have this ZIF-8 mechanism by itself that involves the formation of these amorphous precursors. They dissolve to form this kind of amorphous, more liquid-like material, and that's where these ZIF-8 crystals grow out of. In the presence of the biomolecule, we believe this process is exactly the same, but the biomolecule interacts with its own kind of set of precursors into solution to form this aggregated network phase, which then undergoes a kind of solid state transformation on the surface of these growing crystals. That's why it caps their size out, and that's why you have this kind of really rough surface morphology that we saw in the SEM images at the start, because that's really dictated by the size of these kind of precursor particles. So I won't go through the details, but we also found a similar but importantly different mechanism when you just change the metal ligand ratio from 35:1 to 4:1. It was already known in the kind of biomorph literature that there should be different mechanisms when you change these, but both of them still occur through these kind of amorphous precursor phases. So really what I want to just conclude with here is, what we kind of really nailed down in this work was that in the precursor steps to the formation of these biomorphs are many different types of amorphous precursor particles. And the type of amorphous precursor you get really impacts the final crystal structures that you get. And so what we want to do in the future is to really try and isolate and characterize what these precursors are and learn how to control the precursor to get the types of structures that we're really interested in. So with that, I would just like to finish up by saying thank you, especially to everyone in my group, but most importantly to Alana Ogatar, who really led this effort in my lab. I also want to say thank you to Dima Fishman, who runs the Laser Spec Lab, and the IMRI facilities at UCI, where all our microscopes are, and especially to Li Xing, who runs the cryo microscope there. So thank you all for listening, and I'm happy to take any questions.